So in this video we will talk about the electronic configuration trend in the periodic table. So as we have seen in the previous video that the whole periodic table is divided into 4 blocks, which is called S block elements, P block element, D block elements and F block elements. So in this video we will see about what is the trend of the electronic configuration in the periodic table. So first is so periodic trend is like hydrogen has 1 electron, so the electronic configuration will be 1s. Lithium has 3, 1s2, 2s1. Sodium has 11, so 1s2, 2s2, 2p6, 3s1. Potassium has 19, so 1s2, s, 2s2, 2p6, 3s2, 3p6 and 4s1. So you can see this hydrogen, lithium, sodium, potassium, they are all coming from the first group of element, which is called the alkali metal, hydrogen, lithium, sodium, potassium. And when you will write the electronic configuration of any elements which are from the same group, so you will end up exactly same number of electrons in the subcell. So the metals tend to lose electron to attain the stable electronic configuration. So in case of this first group of elements, you can see the valence cell. Valence means the last cell, or the and valence electron means the last electron which is exist in the valence cell. They are called the valence electrons. So these electrons are the valence electron, 3s1, 2s1 and these subcell are called the valence cell. So these electrons, these metals have a tendency to lose the electron, the outermost one, these one, so that they can attain the stable electronic configuration from the periodic table. So as you have seen, we have discussed about the stable electronic configuration from the periodic table. It means the stable electronic configuration means they must have like 8 electron in the valence cell, like this one. So if you can see, if it will loses the electron once, if sodium will lose the electron, it will attain the electronic configuration like neon, which is more stable. That is why they metals are have tendency to lose the electron, so that they can attain the stable electronic configuration rather than unstable electronic configuration. So this is the first trend of the electronic configuration in the periodic table, that the metal have tendency to lose the electron to obtain the stable electronic configuration like inert gases, right? So next is and here is this example is shows that what is the meaning of a stable electronic configuration. So suppose sodium has lost 1 electron which is from valence cell, then this will become sodium ion. So sodium ion will attain the electronic configuration like the stable neon gas. And on the other hand, calcium, which have the last electron is 2s2, and if it will lose the 2 electrons, it will become calcium ion, and it will attain the 8 electronic configuration like krypton. So helium, neon and krypton, so it will attain the electronic configuration of krypton, so which is more stable. So this is the tendency of the electronic configuration in the periodic table, that metals have tendency to lose the electron to get the stable electronic configuration at the end. Next is we are talking about the fluorine, chlorine, bromine and iodine, and these if you see, they are in the 7th A group, which is called the halogen, and they are coming from the P block elements. So if you write the electronic configuration of these halogen, you will see the last electron will go in the p orbitals. So that is why they are called p subcell. So the non-metal tends to gain the electron to attain the stable electronic configuration. So you can see they have, fluorine have the last in the last cell it has only 7 electron. 2 and plus 5 is 7. It need 1 electron more to become 8, octet rule, which is called octet rule. To attain the octet rule it need 1 electron. Similarly chlorine have 7 electron, it need 1 electron to become 8. Bromine have also 7 electron, it need only 1 electron to become stable. So that is why non-metals have tendency to gain the electron to get the stable electronic configuration. So all these metals and non-metals, they always try to get the stable electronic configuration either by losing the electron or by gaining the electron. So metals have tendency to lose the electron to get the stable electronic configuration, and non-metals have a tendency to gain the electron to get the stable electronic configuration. So this was the periodic table about the stability of the electronic configuration in S block and P block elements. And we will see some exception or some anomalies in the electronic configuration. So this is not anomalies, this is again the example of non-metal when they get the 1 electron extra. So you can see chlorine have last in subshell is the 7 electron total. When it takes 1 electron extra it become 3p6 and this become chloride minus. So this is very important. Whenever you are losing the electron you have to put the charges. Don't forget to write the charge. And if you are you are adding any extra electron, you have to put the minus charge on the elements. Sulfur have 3s2 and 3p4, so it has only 6 electron, that is why it need 2 electrons, and this become s2. So this was about the electronic configuration trend in the periodic table. Let's see what about the transition metal. So if you see that the transition metals are in the center, this one, and they are called D block elements. So and why they are called D block elements? Because the valence electron or valence cell is in the D. So last electron or last subcell is always as a D. So filled cell and half filled cells are the most stable electronic configuration. What does it means? You can see the D subcell have 5 orbitals, 1 2 3 4 5, and this is called 3D. And so 3D means this is, we are talking about the iron. Iron has atomic number 26, and the electrons are 26. So once you will write the electronic configuration of iron, it will be a 1s2 2s2 2p6 3s2 3p6 4s2 3d6. And 3d6 means 1 electron, 2 electron, 3 electron, 4 electron and 5 electron, and the pairing will start first from here. So this is the electronic configuration for the D subcell for the iron. But according to the rule, the filled shell and half filled shells are the most stable. What does it means? It means that you can see iron 2, and then there is one more, and the last cell will be also here 4s2. So s2, which is 4s2. So there are 2 cell. So this iron have, if I will write the iron 2 electronic configuration, so we have to remove the s electron from here, which is the last one. This is the last one. And for the iron 3, which is most stable element electronic configuration in case of iron, because it will attain the filled, completely filled or half filled shell. So now you can see D orbital have here half filled. Each orbital have only 1 electron. So this is 3d5. So this is 3d5 is more stable compared to iron. That is why rust iron always oxidize and it become rust. So rust is more stable than the other form of iron. And so some anomalies, some irregularities occur when the enough electrons to half fill s and d orbitals on the given row. So we'll see some example of this one. For an example, here in case of chromium, you can see this has argon electronic configuration. So how I write argon, I will show you in the next slide. So it has in the outermost, the last electronic configuration is like 4s1 and 3d5. So the chromium have tendency to lose this last electron so that it can attain d5, or it can get one electron from the d5 to complete its last electron, as we have seen in case of iron also. So this occur because the 4s and 3d orbitals are very close in energy, and these anomalies occur in f block atoms with the f and d orbitals as well. So d orbitals and d block element and f block elements have tendency to move the electron in the very close subcell so that they can attain the stable electronic configuration. So next is the core notation. Core notation means the core notation means those which is the interior and the valent electron. For an example, if we write the atomic electronic configuration of for iodine, so iodine, you can see it's in the valence cell, in the p block. This is called halogen. So if you write the electronic configuration of iodine, it will be like 1s2 2s2 2p6. So total, if we count the electron, is 2 2 2 6 6 12 18, and then 18 20 and 30 and 36. So this is 36 electron, and then 10 15 17, so 17. So total is 36 plus 17, 53. So for 53 electronic configuration atomic number, the iodine electronic configuration will be like this. And then you can see up to 36, the atomic number up to 36 is like a krypton. Krypton is just before the iodine. So we can also write this electronic configuration as a krypton. Krypton means there are 36 electrons will be, and you can summarize. This is a core notation, means like a summary of we can summarize the whole electronic configuration in the form of stable gas. So this you can also write like a core notation, and then remaining the electrons. So krypton we can so in core notation we can write only stable gases, noble gases, either helium, krypton, argon, krypton, xenon, radon. That's it. You cannot write any other elements. So must be noble gas or as a core. Let's see some more example in this core notation. So this is the last slide of this chapter. So what is called condensed electron or core electron. So in case of lithium, you can also write helium plus 2 1. In case of sodium, you can also write neon plus 3s1. In case of potassium, you can also write argon plus 4s1. What does it means? It means that lithium is coming after helium. So helium has total 2 electrons and lithium has 3 electrons. So we can summarize this lithium electronic configuration as a helium, which is 2 electron, and then third electron will come as a 2s2. So the elements in the same group of the periodic table have the same number of electrons in the outermost shell. So these are called valence electrons. So here is the valence electron is shown like this one, and the filled inner shell electrons are called core electrons. So these include completely filled D or F subshell, and we write a shortened version of an electronic configuration using bracket around noble gas as a symbol and listing only valence electron. So we list only valence electron, and we write in the summary of the of electronic configuration in the form of noble gases. So this was about the electronic configuration and how to write the electronic configuration, what is the trending of all electronic configuration in the periodic table. So I will suggest to solve as many as possible the questions so that you can understand better this topic, and comment me or question me if you have any problem, or if you have any question you can comment and I will try to answer you. Okay, and have a nice study.